All right. Here we go. So, today we're going to be looking at evaluating limits. All right, that's going to be like our major focus for this unit. We're going to kind of go back to the past, all right, where we were evaluating limits earlier. And in fact, we have some limits here, four of them that we at one time knew how to evaluate, but maybe it's been a little while, so we have to like clean those cobwebs out, and stuff like that, and kind of refresh our memories a little bit. But we did know how to do this at one point. I promise you. Okay. So since this is a review, we'll kind of go through this together. Take it real easy. It is Monday morning. I know we had kind of like a rough weekend, maybe. Who knows? Maybe. Okay. So anyway, let's take a look here at letter A. All right. So when it comes to evaluating a limit, what's kind of like our main strategy that we use? Plug it in, right? Direct substitution in more formal terms there, but absolutely plug it in. All right, if we plug it in, we'll end up with 16 minus 4 minus 12 over 16 minus 16, which simplifies to what? 0 over 0. Okay, and what do we call this form when we result in this? Indeterminate. Exactly right. Indeterminate form. Okay, indeterminate form. We're not really sure what it equals, right? But we have some methods here, right? What is a strategy you can kind of employ here to try and get some answers, though? Maybe is that the best we can do, or is there more we can do here? There's more we can do. What can we do? Factor. Okay, so yes, we see, the numerator factors to x plus 3, x minus 4. And the denominator also factors. It's a difference of squares, right? X minus 4, x plus 4. Okay, so with factoring, what can we then do here?
Cancel them out.
Yes, cancel out the x minus 4s, right? The factors there, okay? And we can say then this limit will be equal to the earlier limit. Because we're merely approaching the 4 there. Okay? And so now we'll try direct substitution. We end up with 7 over 8. And get an answer. All right. All right, so that's like, oh yeah, I remember that, Mr. Witt. That's not that bad. Not that, okay, it's pretty bad. All right, well. Let's try letter B. All right, next one, letter B. Now we're going to take the limit as x approaches infinity. Right, so we're going to go off really, really, really far, to the right there as x gets really, really big. All right. So here, right, we can kind of imagine plugging in infinity too. You can kind of think about a direct substitution here. We're going to take infinity and square it, and then multiply by 3, and then subtract an infinity. But infinity squared is bigger than a minus just an infinity to the 1. So this is still going to go off to positive infinity in the numerator. And then likewise here, we're going to take infinity, square it, so it's going to be even bigger, times 4, minus 16. That'll still be infinity. So we end up with infinity over infinity, which is also something called indeterminate form. It's also indeterminate form. Okay. Infinity over infinity is also indeterminate. Okay. So you may remember, though, what is the limit of this going to end up being? 3/4, right? Okay. Since the degree of the top and the degree of the bottom are the same, we can use the ratio of the lead coefficients, and we know that ultimately the answer here is going to be 3/4. Okay, but let me show you kind of like a way to kind of convince ourselves that this is so, right? Again, we kind of use a table. Let me just show you an alternative way to kind of convince ourselves that this is so. If we take our limit, but if we multiply the top and bottom by 1 over the highest degree term there. So in other words, I'm going to take my numerator, multiply by 1 over x squared, because x squared is the highest degree term, and I'm going to multiply my denominator by 1 over x squared as well, because again, that x squared there, that's the highest degree term in the problem here. When we're multiplying here by 1 over x squared over 1 over x squared, we're just multiplying by, 16, sorry, thank you. We're multiplying by 1 over x squared over 1 over x squared, right? We're really just multiplying by 1, so we're not changing the value of this limit at all, right? We're multiplying by 1. However, when we do this, we'll distribute that 1 over x squared. And by distributing it, so to the 3 terms here, we'll end up with 3 minus 1 over x, right? Because x over x squared would simplify to just 1 over x. And then the 12 times 1 over x squared will be 12 over x squared. All right? And then same deal here. We'll distribute that 1 over x squared to the 4x squared and to the 16. And so end up with just 4 and then minus 16 over x squared. When did we learn this? I'm not saying we learned this. I'm saying that this is an alternative way to think about how we can evaluate the limits here. So perhaps you saw this before, but perhaps you did not. Okay, but this is an alternative way to kind of evaluate this. Okay. So as x approaches infinity, right? Well, this 1 over x, what will it approach? 0, right? Because our denominator is going to get humongous, and we're going to take that 1 and divide by a really big number, and so it's just going to go to 0. Same thing with the 12 over x squared, right? That goes to 0 as well. Same thing with the 16 over x squared. The 3 and the 4, what happens to 3 as x approaches infinity? It's just 3, right? And what happens to 4 as x approaches infinity? There's no x there with it. It's just 4, right? So we end up right with 3 minus 0 over 4 minus 0, so the 3 over the 4 there. Like, you know, you guys are able to pick out without doing all that work there. Okay, but I just want to show you an alternative way to kind of see that. Okay, an alternative way to see it. All right, so not too shabby. Questions on any of that so far? Pretty easy, hopefully. Okay. Well, so next one we got here, limit as t approaches pi over 2 of 1 minus the sine of t squared over t times cosine t. So again, we can try a direct substitution here. 1 minus, let's see here, sine of pi over 2 is 1, so 1 squared will just be 1, over, and then we'll have pi over 2 cosine of pi over 2, 0. And so we end up with 0 over 0. Oh man, another indeterminate form. Right, it's like I'm trying to lead up to something here. Or Mr. Goff is, because he wrote these notes. All right, so, right, that's not very helpful, but any ideas about what we can do here to help ourselves out with this? Yeah, so 1 minus sine squared t is the same thing as a what? Cosine squared. It is a Pythagorean identity, right? It's a manipulation of it. Normally we say sine squared t plus cosine squared t equals 1, but if you subtract the sine squared over, yeah, then it'll just end with cosine squared t. Oops, cosine t like that. And now because we have this, what can we do? Cancel out the cosines, that's right. So we'll have cosine t over t. Okay, and now we can plug in that pi over 2. It's a really sloppy pi over 2. All right, and so we'll end up with then cosine of pi over 2, which is 0 over pi over 2. So we end up with just an answer of 0. Next one. Yes, very good. The next one is indeterminate if you plug in as h approaches 0 there. All right, so I guess hopefully. Yeah, anyway. So what is this limit? Oh, no. Yes. Kyle? So, okay, it's the, what is it asking us to do? What is this limit? When we see this, this is asking us to do what? Yeah, Sean? It is the limit definition of the derivative, and it's the derivative of just cosine x, like Kyle was saying. Exactly right. So what is the derivative of cosine of x? Negative sine x. Yeah. Okay, yes. Okay, remember this is the limit definition. Okay, if you remember months ago, okay, last year, months ago, we were evaluating these by hand, right? And they were awful. This one you didn't evaluate by hand, though, because it's kind of, well, anyway. But then we learned the shortcuts, right? And so now when we see this limit definition, remember that it is not expected of you to actually go through the whole process of like simplifying and plugging in x plus h and plugging in cosine x and subtracting and stuff like that. Realize this is the definition of the derivative. The definition of the derivative, right? There's our minus f of x. Remember, this is the f of x plus h minus there's our f of x. So this thing, cosine of x, is our function, and we're going to take its derivative. F of x is cosine of x, not negative cosine of x, right? Because for the limit definition, you have to have minus f of x. So minus cosine really means our function is positive cosine, and its derivative then is negative sine of x. Okay. All right, negative sine of x there. All right, And then lastly, our last kind of technique, because that kind of illustrated, several of the techniques that we have. Our last technique that we have for evaluating limits is to use our calculators. So what about something like the limit as x approaches 0 of e to the x minus 1 over sine of x? If you can't figure out a way to simplify this, then you can use the table/graph to evaluate your limit. All right, so why don't you guys go ahead, get those calculators out, see if you can remember how to do that. All right. I will do the same. Very good. The sound effects help. Are you just pushing random buttons because it sounds like you're pushing just random buttons there? I figured you out. Busted. This is still calculating. If you push the buttons, it helps to go faster.
It's not all what I was doing. You just look silly.
You're right. I should stop.
Let's just connect up right now.
Still have that?
Yeah, Patrick still hasn't come to me. Get it?
Pulls down and gets left to wake up.
Like, actually, there's a Bluetooth button back. What?
So he brings computers to school.
Are you serious? Like, here at this school?
Yeah. He like his screen shares computer to like his Xbox or something. Microsoft.
Like play it like remotely, you're saying, or something?
So like you could like see his Xbox screen like on his computer.
Right. But his Xbox could be like home or something like
Yeah,
that.
so the Xbox was at his house and I guess he was playing, which doesn't make sense. I didn't think the controller could go online.
Yeah, that's interesting. I mean, there used to be like this like company, I forget what it was called. It was like a cloud gaming company where you wouldn't buy the hardware. They would stream your inputs to their own machines and like this server thing, and then they would stream the game's video to you, and so you could then ostensibly like play games without having to have like this ridiculous amount of hardware. You could just like stream back and forth. The problem is, of course, if you like have any sort of lag, then it just throws it off. But, so I don't know. So, but right, exactly. So, all right, Sarah, what did you get for the limit here? 1. Great job. It is 1. Okay. Now, I want to point something out here, right? If you forgot how to do this, remember you type this into your graphing calculator. Ooh. Oh man, this is just going crazy. Let's see if I can fix this up. Okay. Sorry. There we go. Remember, you can put this in your graphing calculator, type in the function, make sure that you have parentheses around the numerator. Not a bad idea to also put parentheses around the denominator, although it's not necessary for this particular one, but anyway. Go to your table, right, and you're going to type in something that's close to 0. So I put in like 0.000000001, okay, and the calculator gave me just 1. Is this enough analysis, though, to say that the limit is 1? Did I do enough work here to say that the limit is 1? No. What do I still need to do? I need to approach from the other side of 0, right? If you only did it from one side, you potentially, all right, gave the wrong answer. Now, obviously, it's going to end up being, so if I do negative 0.000000001, right, now you can say, aha, the overall limit is 1, okay? If the left-hand and right-hand limit disagree as you're approaching 0, then the limit does not exist. That's right, just like Lindsay Lohan said in Mean Girls, all right? It's a different kind of limit there, though. I think eventually we'll be able to evaluate that limit at the end of Mean Girls too. So we'll maybe like show you that or something. I don't know. Maybe it won't be that exciting to you at that point. Anyway, moving on. Wait, I watched the whole movie just for that one application. Yeah, I hear you. Anyway, maybe. Anyway, L'Hopital's rule. Okay, and that's how you pronounce it. L'Hopital. L'Hôpital, okay? It's got like the O with this little hat on it. Okay, yeah, it does look like that. There's no S though. Right. So,
There is an S.
at the very end, but not in the middle where hospital has one. But anyway, let F and G be yeah. Let F and G be functions that are differentiable on an open interval AB with C, okay, except possibly at C. Okay, so let me reread that one more time here. F and G are functions that are differentiable, okay, on an open interval AB with a number C that's in that interval, except they may not be differentiable at that single point C. Okay, so if the limit as x approaches C of f of x over g of x is 0 over 0, then the limit as x approaches C of f of x over g of x equals the limit as x approaches C of f prime of x over g prime of x. Okay? So, what that means is, when you are trying to take the limit of like a rational function, we'll say, a function over another function, if when you evaluate that you get 0 over 0, all right, one way you can kind of like help yourself still evaluate this limit is to take the derivative of the numerator and the derivative of the denominator and then evaluate the limit as x approaches C of those derivatives. Okay? They will be the same value. It will be the same value as you approach that C. Okay? This is not saying take the derivative of the rational function and then take the limit. This is saying take the derivative of the numerator divided by the derivative of the denominator. Okay? So this is like the way we would want the quotient rule to be, right? We want the quotient rule to be just take the derivative of the numerator, take the derivative of the denominator, and then evaluate. Okay? But that's not the quotient rule, right? So we have to be a little bit careful here. All right? This result also applies if the limit as x approaches C of f of x over g of x is some other indeterminate form. That is positive infinity over positive infinity, or positive infinity over negative infinity. You get the idea there, right? Or plus or minus infinity, or minus positive, or plus or minus infinity minus plus infinity. 0 times infinity is also an indeterminate form too, right? Because 0 times infinity, what does that equal? You're taking something that's nothing, but then multiplying it by something that's infinite. So it's like, what would that equal? Indeterminate, right? So, etc. So again, there are two major mistakes that are made when doing L'Hôpital's rule, okay? Major mistake number one, you first must verify. So in other words, the mistake is not verifying indeterminate. Okay? You must show that the limit is indeterminate before you can apply L'Hôpital's rule. You must show that. Must show it. So you can't just like willy-nilly start taking derivatives of limits now and evaluating them, okay? You first must start with a limit that is indeterminate. Then you may apply L'Hôpital's rule to it, okay? All the limits that we did on the front here, right, except for, well, I guess even including, all four of these limits on the front here, right, those were all indeterminate initially, and so you can apply L'Hôpital to all of those. So, first verify that it's indeterminate, and then second, remember that this is not a quotient rule. Okay, it is not a quotient rule. So do not use the quotient rule here. All right. So, with that in mind, let's take a look back at that problem we just did on our graphing calculators. In fact, a problem that we could not have done prior to this point without our graphing calculators, right? If we plug in 0 using a direct substitution, we end up with e to the 0 minus 1 over sine of 0, which is then 1 minus 1 over 0, which is 0 over 0, right? Indeterminate form. Okay, indeterminate form. You don't need to write that. You can just show 0 over 0. You don't need to write that that's indeterminate form. It's understood. But what we do need to do is to then say, L'Hôpital applies. Yes, I believe that is necessary. Okay, to show what you're doing there. Okay, and so then we'll say the limit as x approaches 0. And now we'll just take the derivative. Okay, what is the derivative of the numerator here? E to the x. What's the derivative of sine of x? Cosine x is right. All right. And so now we will try direct substitution and see what happens. e to the 0 is going to be 1. Cosine of 0 is 1. All right, very sleepy people this morning. All right, so then 1 is our limit there, right? We get that without having to use our calculators. But it confirms what we got with the calculator, too. All right, so let's take a look then at some of these other problems that we did earlier, right, on the front. So for example, this one, right, we already established that it was equal to 0 over 0 on the front if you just do a direct substitution. So again, we will apply L'Hopital. Okay, you can say L'Hopital applies, you can say apply L'Hopital, however you want to say it there, okay? So, but do acknowledge that we're going to be applying that here. So we'll say the limit as x approaches 4, and then again, just take the derivative of the numerator, 2x minus 1 over 2x. And now if we do a direct substitution, 2 times 4 is 8, minus 1 is 7, 2 times 4 is 8. 7/8, exactly what we got on the front. All right. So what does this mean? This means that you don't need to factor and cancel if you don't want to. You have an alternative strategy. All right, you have an alternate strategy here that will allow you to evaluate limits. Okay, maybe even faster, right? Because we've been doing the derivatives so much that this maybe is even faster for you there. Okay, so you can just take the derivative of the numerator, take the derivative of the denominator. All right. Same thing here. We can apply L'Hopital to this too. Again, we know this is going to equal 0 over 0. We can apply L'Hopital to this. Keep in mind here that h is our variable. Okay, that's what we're trying to evaluate. Okay, but we'll take the derivative here. So we're going to take the derivative with respect to h. Okay, because we're trying to evaluate h, just like over here, right? We were taking the x was our variable, and so we took the derivative of all this with respect to x. Over here, we're going to take the derivative with respect to h, which means that x we're going to treat like it's kind of like a constant, okay? And so the derivative of the cosine, well, what's the derivative of cosine of something? Negative sine of that something times the derivative of the something. X is not our variable here, so we're not going to take the derivative with respect to x, so that's just going to disappear. It'll be 0 plus, and then the derivative of h is 1. So I'll just do it 0 plus 1 like that. Times the derivative of what's inside, right? Using the chain rule there. Minus the derivative of cosine of x, it's going to be 0. Okay, all over, and the derivative of h with respect to h is 1. Because, again, our variable here is... Our variable here is h. And so when we take the derivative, we'll do it with respect to h, and that makes x just a constant in this case. So the x will, when you take its derivative, will just be 0. And so cosine of x is a number, so its derivative will still be just 0 there. All right, now we can direct substitute in 0. 0 in for the h, 0 in, well, there's no other h to plug it into, so it just becomes negative sine of x plus 0, which is then just negative sine of x. Okay, so it even works for that. Okay, negative sine of x there. Okay. Try this one on your own. I was going to do it, but Mario wants to do it, so go ahead, Mario. Give this one a try. All right.
I bet L'Hopital doesn't apply on this one.
You bet? We'll see. I see what you're thinking.
So if it's multiple choice,
Smell what you're cooking. What's that?
If it's multiple choice, we still have to it applies.
No, if it's multiple choice, right? You can like kind of just, do the minimum amount of work that you need to there, I guess. Good question, Lander. Just factor it? Okay.
Mike, circle A. No, Mike, A. Yeah. There you go, Mike. See, Mike, I got you on that. Like on the AP test, we'll have kids, we'll go. I'll be A.
Go.
Okay. I'm not saying who's right or who's wrong here. Okay. Just look into it.
So there we go. That and precision.
We have to go to the bathroom and be like, okay. He's like, never mind.
Yeah.
He's like, I have to go to the bathroom.
That's the high score is
You just have distracting all messages.
what if we just use our tangent?
You can't use arctic.
I know.
I got B too, but that Mark don't want to change his A. Let's see what it is. I got B. I'm going B.
So you changed your mind.
From B to A to B, yeah.
BAB?
Bab.
Bab. Okay. You're not going to let Mario influence you?
No.
Peer pressure?
No more.
No more.
Mario's in charge of me no more.
You were freed.
What you like,
The
Mike?
chains are broken.
I like the goods, Mike. Shh. I catch those dubs, Mike. You gotta stick with me, buddy.
I'm gonna get the one that wins
Yeah. Christian, what did you get here for letter C? Letter B is right. Okay. It is letter B. All right, so first of all here, right, you want to check to make sure that L'Hopital's applies. Granted, you need to write that, but you do want to check it because if you can't apply it, then you can't use it, right? So we do end up with an indeterminate form here, 0 over 0.
I forgot the 2.
Okay, yeah, don't forget the 2 when you take the derivative, right? Chain rule here. And again, this is crucial right there, right? 2 cosine 2x, okay? Derivative of sine's cosine times what's inside. So 2 cosine 2x there.
I think we're done with that.
So, questions on any of that? You end with 1 over pi. 1 over pi. No questions? Okay. So yeah, be careful with that, taking that derivative, right? Those little chain rule things are easy to miss, especially when they look so simple. You know, sine of 2x, how hard can it be? But don't forget that cosine, or the multiply that chain rule there, the 2, okay? Okay, moving on. So let's take a look at a few more here, right? So now we're going to be evaluating limits that approach infinity as x approaches infinity here, okay? Stuff that we, again, have, we saw a problem like one of these maybe on our little practice quiz thing that I gave you there, a pre-test thingamajigger. So anyway, taking a look at this, right, we'll try a direct substitution in here. So we're going to plug in infinity, so to speak, right, over infinity. All right. The natural log of infinity continues to increase without bound, okay? Slowly but surely, it does continue to increase. There is no upper limit there. And so this is essentially saying infinity over infinity, which means what form is this? Indeterminate, right? Okay, so we establish it's indeterminate. We can say, L'Hopital applies. Okay, and again, I'm not trying to be pedantic here. I'm pretty sure that you need to write that little phrase. Okay, those 2 little words there. Yeah.
What if I spell it wrong?
If you spell it wrong, that's probably okay as long as it's like,
At least like legible.
yeah, okay. Yeah, like if you write like La Hospital, I'm sure you won't be the first La Hospital as the AP graders see, and they'll chuckle to themselves and then they'll just move on. All right. So that means we're going to take the derivative here, the top and the bottom. The derivative of the natural log of x, 1 over x. The derivative of x, 1. Again, not a quotient rule. Not a quotient rule here. We're just taking the derivative of the numerator, derivative of the denominator. Okay, now we'll plug in infinity. We have 1 over infinity over 1. What does 1 over infinity simplify to be? 0. So it's 0 over 1, which is then just 0. Okay. Let's try the next one here. All right, again, let's simulate kind of plugging in negative infinity here. We'll have negative infinity squared times 3 plus 7 times negative infinity. So we're going to have positive infinity, right? A negative infinity squared is positive now, times 3. And then we'll have negative infinity times 7. So what's going to win out here? The positive infinity that we get from this or the negative infinity that we get from this? The positive infinity will because it is negative infinity squared. Okay, it's going to be always bigger than this, and so it will make it a positive infinity over, and then this is going to be a negative infinity squared, so positive, but then it's times a negative 4, so it's negative infinity. Regardless, this is what form? Indeterminate. Okay, so we can apply L'Hopital. Okay, and again, the hat goes over the O. Okay, the hat goes over the O. All right. So, again, we're taking the limit as x approaches negative infinity, and we'll take the derivative of the numerator there. So 6x plus 7 over the denominator, negative 8x. And now we'll direct substitute, and what do we end up with? Well, in this step, we end up with an indeterminate form again. We have to apply L'Hopital again. Now, granted, yes, could we have just used our, rules that we know, where the degree of the top is the same as the degree of the bottom? Yeah, we could have here. But why make it easy when you can make it harder? Right, exactly. Yeah, we're not in the business of that. So then we take the derivative. We end with 6 over negative 8, which is negative 3/4. So you're right. It is negative 3/4 there. Okay, right. So is L'Hopital, necessary here? No. Okay, you could have just used your degree of the top, degree of the bottom are the same, and so you take the ratio of the leading coefficients, negative 3/4. Okay, so you can still use those other methods, but don't forget L'Hopital does, work as well. All right, letter C. So if we try plugging in infinity here, we're going to end up with, again, infinity times e to the negative infinity, which is infinity over e to the positive infinity, which is then infinity over infinity, right? So it's indeterminate still. Okay, still indeterminate. So we're going to say that L'Hopital applies. Okay, and we'll take the derivative. And let's make sure we understand here, right? This is the limit as t approaches infinity of t squared over, t squared over e to the 2t. Right? We can rewrite that as a fraction, right? T squared over e to the 2t. And now I'll take the derivative there. So the derivative of t squared is 2t, and the derivative of e to the 2t is
e to the 2t times 2.
Yeah, 2 e to the 2t or e to the 2t times 2, yeah. Okay, we plug in infinity here, and we end up with infinity over infinity again. So we will apply L'Hopital one more time here. And we end up now with just 2 over 4e to the 2t. And we'll have 2 in the numerator over infinity in the denominator, right? Because 2 times infinity is infinity. E to the infinity is infinity. Times 4 is still infinity. So what does 2 over the infinity equal? 0. Exactly right. Okay. Let's try this next one here. All right. Letter D. We'll plug in infinity here. Infinity squared is infinity plus 5. Infinity squared of infinity is still infinity. So we have infinity over infinity. So again, it's indeterminate. L'Hopital applies here. It is annoying. I agree. Okay. So we'll take the derivative, right, to apply L'Hopital. So let's see. Natural. Sorry, limit is x approaches infinity. So, okay. Remember, this is x squared plus 5 to the 1/2 power instead of the square root there, if you want to say. And so this then, the derivative is 1/2 x squared plus 5 to the negative 1/2 times 2x. Good. Over 1. Which we manipulate this, right? So 1/2 times 2, those are going to simplify and just cancel out. And so we're left with the limit as x approaches infinity of x over x squared plus 5 to the positive 1/2. Okay? Since it was to the negative 1/2, if I move that into the denominator of the x there, it'll be x over x squared plus 5 to 1/2, like that. Okay? If we plug in infinity, what's going to happen here? Still indeterminate form. Yeah, so we get to apply L'Hopital again. So apply L'Hopital. Okay, and so we end up with the limit as x approaches infinity of 1 in the numerator over 1/2 x squared plus 5 to the negative 1/2 times 2x. Oops, I'm off the screen. There we go. All right, which then results, well, let's see here. Again, the 1/2 and the 2 can simplify. We will have limit as x approaches infinity of 1 over x squared plus 5 to the 1/2. Like that, right? Okay, so the x over the x squared plus 5 to the 1/2, that's all in the denominator. But then we have 1 over that, so let's simplify that, right? So it's 1 over, so we can just do the reciprocal here and make it the limit as x approaches infinity of x squared plus 5 to the 1/2 all over x. Okay, why do you give up? Because it never ends. Exactly right. Yeah, if we keep applying L'Hopital here, okay, it's going to be a circle. So L'Hopital is useless. Okay, isn't that fun? Doing things, digging a ditch and then filling it back in, and then digging a ditch and filling it back in, because that's what we're doing there. Okay, it never ends.
Use substitution.
Okay, so we know how to evaluate this, though, right? You guys were actually, if you remember back in the day, you were able to evaluate this prior to learning about L'Hopital, right? Prior to now confusing ourselves with this new information, right? What can we consider the degree of the numerator here to be? 1. And what's the degree of the denominator? 1. Okay, we can consider the numerator's degree to be 1 because it's a square, but underneath a square root. Square rooting a square, right, is just 1. And so, since the degree of the numerator and the degree of the denominator are the same, we can take the ratio of the lead coefficients. What's the lead coefficient here? 1. Square root of 1 is still 1 over, so the answer here is 1. Yeah. So just 1. Okay, using the ratio of the lead coefficients and stuff like that. Alrighty. Neat. All right, so I think I'm going to have you guys try these on your own here. All right, you got some time. You don't want to do C? All right, well, I'll give you like 5 minutes or so, and then we'll go over them ourselves. Bless you, okay? I'll give you like 5 minutes or so here. Try all of them, please. A, B, C, D, E, F. Yeah, in 5 minutes. I know I maybe didn't give you enough time, but at least you'll get some time to wrestle with them for a little bit bigger. Okay, so A, B, C, D, E, F. I did. So yeah, give those 6 a try. I'll give you, like I said, 5 minutes or so, because we are running short on time here. Gabe, I'm going to put you in for set today for the quiz, yeah? Okay. Caitlin, you said today, right? Okay. Julia, you as well?
I say after school.
After school? That's fine. Okay.
But I didn't want to go to set.
Don't fail.
Gotcha. Madison, set today for the quiz?
I've taken AP my math test again.
Okay, that's fine, yeah. Okay. Well, okay, so when we get here, let's get the upper limit that gets plugged in, actually ends the sign of x. Glad you're thinking about that. That's good.
The answer's fine.
The derivative and then
Like 2 or 3 more minutes here. 2 or 3 more minutes. No rush, but what's that? Why are you taking the integral sign? Oh, you want to simplify it that way? I see what you're saying. Then yeah, you can do it that way.
Is that not the way?
Well, you could also, yeah, that's. I guess that is the way, if you want to. But you could also use L'Hopital's rule there. You can take the derivative of integral. Remember, second fundamental theorem of calculus.
Getting mad.
You can take the derivative of an integral.
okay, so I knew there was zero, but I forgot what that was. So like yes.
You're dumb.
So,
I'm scared, bro.
Still gonna get the derivative. I'm on, yeah.
It's 0.
This I might be making things more confusing here. But we'll see. Okay, let's say you want to take the derivative of this. Okay, then the derivative of integral, they kind of cancel each other out. So you end up doing nothing to this except plugging in the upper limit minus the lower limit. So it'll be
0. Pi. 0 but pi is 0. Tell us it's not twice.
okay. So in other words, in this case, it'll be
-1.
this is sine, right? So you're gonna have
I didn't do It's just
right. You see what I'm saying there? The upper function is x, so x gets plugged in times the derivative of x1, so sine of x times 1 minus pi is the lower limit. That's the function, so you plug in pi, sine of pi, but then it's times the derivative of pi, which is 0. So the lower limit disappears. Height.
Oh. What was that, Mr. Witt?
What?
You said I?
Height.
0.
Okay.
Or bacon. I do that in my car all the time. Wait, how does L'Hopital apply? Okay.
Okay. So for letter A, they can keep working if you're fine there. Letter A, you should have gotten 0, okay? And just thing I want to point out, right? L'Hopital does not apply to every limit, okay? So don't make it fit something that it doesn't fit, right? You need to have indeterminate form. If you do a direct substitution here for letter A, you get 0 over pi. That is not an indeterminate form. 0 divided by pi. That 0 divided by pi is 0, okay? Sometimes my brain mixes things up. Okay, moving on. So now, this one, we do get indeterminate form. So we will apply L'Hopital. Okay, and so we end with cosine x over 1. And so we get negative 1 then. Right, cosine of pi is negative 1. So negative 1 over 1, negative 1. Okay, here, a little bit funky. We have an integral and a limit. Yuck. But if you do a direct substitution, the integral from pi to pi of anything will be what? 0. So you're going to end up with 0 over, and then pi minus pi is 0. Question, Sean?
I have a question from Bob.
Okay, sorry.
How do you get negative 1 from that?
The cosine of pi is negative 1. Cosine of pi is negative 1. So then again, we apply L'Hopital here. Okay, apply L'Hopital. And so we take the derivative. Now, the derivative of an integral, second fundamental theorem of calculus, we end up with just sine of x over, and then derivative of x minus pi, 1. Plug in pi, sine of pi is 0 over 1 is 0 for your final answer. Okay, so C is 0. Questions on that? Okay, if you decide you have a question, let me know. All right, next one equals 0 over 0. So again, we will apply L'Hopital. It's indeterminate. Okay, hat on the P. So we take the derivative here, limit. As x approaches 0, derivative of cosine squared is 2 cosine of x times the derivative of what's inside. Derivative of cosine is negative sine. Derivative of 1, 0. Derivative of e to the 3x is 3 e to the 3x. Derivative of 3x is 3, and the derivative of 1 is 0. If we do a direct substitution now, what do we end up with? Womp, womp. All right, but we have to take the derivative again. This better not be one of those infinite ones, Mr. Wid, or we're going to be really mad. Already really mad. Doesn't even matter anymore. All right, so let's see who'll do the second. So negative sine of x times the derivative of the first. Derivative of 2 cosine is negative 2 sine of x. What's the first? 2 cosine x times the derivative of the second. Derivative of negative cosine is negative, sorry, derivative of negative sine is negative cosine x. All over the derivative of this would be 9 e to the 3x. Okay. Now if we plug in 0, sine of 0, sorry again? The derivative of 3 is 0. Okay. So that's okay. So then plug in 0 here. Sine of 0 is 0 times 2 times sine of 0, which is 0. So that's 0. Cosine of 1, sorry, cosine of 0 is 1. Cosine of 0 is 1, so it's negative 1 times a positive 1 times a 2. So we get negative 2 over 9. Negative 2 ninths. Okay, negative 2 ninths there. Okay. Letter E, it's multiple choice, so I'm going to do a little bit more quicker work here just because it's multiple choice. We'll take the derivative. We don't need to apply L'Hopital's here because it's multiple choice. They're not going to check your work. So we'll say 7 minus cosine x over 2x plus 3 cosine 3x. Okay. Plug it in. You get 7 minus 1 over 0 plus 3. So we get 6/3 or 2. So letter E is letter B. Okay, 2 there is our answer. Ugh, it was messy. And the last one. All right, we apply L'Hopital's for this infinity over infinity. Okay, and we're going to get 500 x to the 99 over e to the x. And then again, we plug that in, we get infinity over infinity. Take the derivative again. Limits x approaching infinity of, well, let's just dot that. And we're going to have 500 times 99 times 98 times times 2 times 1 all over e to the x. which is just going to go to 0. Okay? So the idea is, obviously, you're not expected to take the derivative 100 times here, right? The idea is to recognize that we're going to keep multiplying those powers out until our x eventually disappears and just becomes a 1. All right, and then we'll have that over e to the x. We'll have some product over e to the x, but it's going to be e to the infinity, and so it's going to go to 0 because the denominator gets really, really big with respect to the numerator there. All right? Questions on any of that? All right. Your homework is on Google Classroom. Hopefully problem set 12 will also be posted by that point too. Please make sure you get the homework to me if you didn't turn it in, or same thing with the problem set 11. And then finally, your test review is also posted to Google Classroom as well if you want to get a head start on that, okay? If you didn't do so hot in the quiz, I'd highly recommend you start looking at that review, okay? Any other requests for set today? Any other requests for set?
Can I come in?
Yes. Aubrey. Okay, I'll take that. Thank you. Yeah, of course, Julia.
I gotta say I'm a little better because I got everything right on the quiz.
Bye, guys. Have a good day.
One question that I didn't get the question.
Yeah, I know. I'm sorry, Cassie, but that's good. Yeah, see?
I got it. That's fine.
Right. I mean, that's frustrating. I get you, but you did a good job, Cassie. You really did. I was really happy to see how you really did. Okay.
Does tomorrow after school work for taking the test?
If you'd like to, yep, that should be fine.